Hello, everyone. We are going to continue our discussion on electron beam and specimen interaction. And in the last class, we were discussing X-rays and how they are generated from the specimen when the electron is incident on it. And we're going to continue and learn a bit more about the different kind of other processes that can occur and in what kind of samples these processes are useful in getting and extracting information. Okay. So we have the EDS that we understood in the last class. These are the characteristic peaks which are riding on top of the bremsstrahlung white noise or X-ray radiation, which is the continuum also, right? And then we also discussed about how there is a difference in the intensity of the respective peaks depending on what is the source of the X-ray, whether it belongs to an L series or a K series, right? And also we spoke a bit about the relative transition probabilities and the relative weight of the lines and what implication it has in terms of the sample or the specimen you are investigating, right? So depending on the Z number, you can have either a single line or you can have multiple lines um, um, in the EDS spectra. Okay, and the intensity of these lines depends on the um, ionization of that specific shell or the probability of ionization of that shell, right? So today we are going to talk a bit about X-ray absorption. So you have the X-ray which is generated as a consequence of the electron beam ionizing the atom, right? And then that X-ray can either escape and you can detect it with your EDS detector um, and get the EDS spectroscopy, or that X-ray can also be absorbed in the specimen before it leaves, either partially or completely, right? So X-ray is basically a photon, and if it is absorbed in the specimen, typically it results in the emission of an electron, which is also called a photoelectron, and the process is called a photoelectric absorption, right? So the electron is ejected if X-ray energy is slightly more than the critical ionization energy of the shell. So I'm going to talk about that in the next few slides. The amount of energy that is or X-rays of specific energy are absorbed more than others, and then and that is related to something called the mass absorption coefficient. But the whole idea is that you have these X-rays that are generated, and as they propagate in the specimen towards the surface, they continuously lose energy, right? And they lose energy by the simple relationship here, where I naught is the energy of the X-ray as it was generated as a consequence of the ionization of the shell, and then as it is propagating through the sample. So here is a schematic. So T is the thickness of the sample. So think about it like this: you have the X-ray that is generated at some interaction at some location in the interaction volume, and typically T is somewhere between 1 micron or maybe up to 5 microns, right? And the X-ray is propagating, so it can make its way out of the sample, which is on towards the right, if it travels the entire distance T. But while it is doing so, it is losing energy um, given by this relationship or the intense. No, I'm sorry, it's not losing energy; it's losing intensity given by this relationship. Okay, so where rho is the density of the specimen. So if you have a higher atomic number sample, the loss of intensity is going to be a lot faster versus a low atomic number sample. And the relationship mu over rho, mu is the absorption coefficient. That is something very important, which is also called the mass absorption coefficient, and it is given by the units of centimeter square per gram. So what does that really mean? So let's take a look at this image, this picture here on the right, the figure here on the right hand side. You have X-rays on the energy of the X-ray plotted on the x-axis, and then you have the mass absorption coefficient in the y-axis. So typically, the X-ray is losing energy exponentially, which is given by the relationship right here. Yeah. And so the absorption of the X-ray, or the probability of absorption of the X-ray also drops because the X-ray is losing energy. Now, as the X-ray is losing energy, if the energy of the X-ray is slightly higher than the energy of the critical ionization energy of a given orbital electron, then suddenly there's a jump in the mass absorption coefficient. So what it basically means is that as the X-ray is propagating to the sample, through the sample, it is losing energy. But if the energy of that X-ray, while it is losing it, matches or is slightly higher than the ionization potential of an electron in a given orbit, then that is absorbed. As a result of which, the mass absorption coefficient goes up. Right? There's a discontinuity here. Okay, so this is also sometimes referred to as X-ray absorption edge. So you have X-rays that are being absorbed, um, given by this figure here. Yeah. So you have this background noise is your Bremsstrahlung, that's the continuum, and then you have your characteristic X-rays, and then if you if there were no X-ray absorption or photoelectric absorption of X-rays, then you would imagine that this continuum would tail off like this, rather than show a sudden drop in the edge. So that is the edge I'm talking about, which is basically corresponds to the energy of the critical ionization of a given orbit in the atom, right? So when the X-ray has an energy close to the um, critical ionization energy, slightly higher than that, then that energy is transferred into the electron, and the electron is emitted out of the sample. So the electron from the X-ray goes to emitting the electron out of the atom, uh, which is why you see the sudden drop in the absorption edge. Okay. So this is very important, because the X-ray absorption edge gives you very critical information about the quality of the sample, and it changes quite drastically depending on the composition. So for example, here is your absorption coefficient for iron, and here is the absorption coefficient for iron oxide. So if you take the mass absorption coefficient of the respective oxygen and iron, you can do a additive weighted mass absorption coefficient, and then that results in an absorption edge which is different from that of iron. So you can distinguish from the database if your sample has oxygen in it or not, or even if it does, at what composition. So you can do an elemental analysis of the atomic weight of iron, or the percentage of iron present in your sample versus the percentage of oxygen, depending on the location of the absorption edge, right? So another possibility is that the X-ray that is absorbed into your sample results in the generation of more X-rays, which is also called X-ray fluorescence or secondary X-ray generation. Okay, so let's try to understand this. You have the incident electron beam. The incident electron beam ionizes an atom, as a result of which you have the inner shell ionization, and then it tries to stabilize and go to its lowest energy. As a result, it emits an X-ray, right? So the X-ray that comes out of the atom, the first atom, is your primary X-ray. Now this X-ray can have sufficient energy to knock off an electron from a different atom, from its orbital, and then the process continues where you have another bunch of X-rays generated in the second atom, right? So that is what is the X-ray fluorescence, where if you have X-ray generation from the incident electron beam, then that is your primary X-ray fluorescence. And then if you have X-ray generation from the X-rays that were generated from the incident beam, that is your secondary X-ray fluorescence. Okay, and because it is quite similar to the primary X-ray generation, you can also have characteristic fluorescence, or you can have continuum fluorescence. Basically, these two processes coexist, right? So let's take a look at this. You have your incident electron that is coming from the beam. It knocks off an electron from the K shell, right? So this is the knocked off electron, or this is basically an inelastic scattering event. So this electron will either be detected as a secondary electron, depending on whether or not it makes its way out of the sample or the specimen surface. Because this was knocked off, now the L electron from the L orbital replaces it to minimize the energy of the atom of element A, right? And as a result of which you have your X-ray that is being generated. Now, while this X-ray is traveling through the specimen, it is losing energy given by the exponential relationship that we saw in the previous slides, and then this is the corresponding mass absorption coefficient, right? Now, as it is losing energy and traversing through the sample, it encounters an atom of element B, and then this X-ray can knock off an electron from the K shell of element B, right, from that atom. And now this atom is the energy of this atom is basically the difference in the energy of the X-ray after it had traveled through a thickness T, right? So the energy of this X-ray is going to be slightly lower than the energy when it just left the element A, and then that's going to be the difference of that energy minus the critical ionization energy of this electron in the K orbital of element B, right? So the energy that with which this electron is knocked off is not going to be characteristic of either element A or B, because you cannot really quantify what will be the energy of X-ray photon or immediately before it is hitting element B, because this could be X-ray photon that is coming from an element A that is at a distance T or T1 or T2, various distances, right? So you really don't know. You basically have a spread in the energy of the electron that is knocked off from the orbital K, right? And as a result of which, this process that happened in element A is going to again happen in element B, and then you have generation of a secondary X-ray, right? So the primary difference is that the the source responsible for knocking off the electron in this case was the beam electron, versus in this case was the X-ray that was generated from the first incidence or the first event, right? And also keep in mind that this X-ray photon energy, before interacting with the electron here, lost energy while it was moving from element A to element B. Okay. So what I want to stress on is that the X-ray fluorescence and the photoelectron generation is not characteristic. That means it's basically a continuum. Okay, so there is another parameter which basically explains or tries to quantify the generation of the primary X-ray and the secondary X-ray, which is basically the ratio of the direct and of the indirect over the total X-ray fluorescence, right? So direct X-ray radiation would be the initial X-ray generated from the beam electrons, and then if you take the sum of the X-ray from the beam electrons and the secondary X-ray, that would be your denominator. And various studies have been done for different atomic numbers. This is just to give you an idea that up to 40% of the X-ray that you detect for a given atomic number could be from indirect X-ray generation. So that is how complex the analysis becomes due to the various interactions that occur simultaneously. Okay, and then finally, I want to talk about Auger electrons. So the Auger electrons are also electrons that are knocked off the sample, right? But the primary difference between Auger electrons and the photoelectrons generated is that this, in case of photoelectrons, it is not characteristic, but Auger electrons are. So what that means is you have the beam electron that hits the K shell, ionizes the atom, and then and another electron from a different orbit replaces the K shell electron, and that energy goes completely into knocking off an electron from the outer shell of that specific atom itself, right? So this is a non-radiative process, right? And then the energy with which the Auger electron comes out of the sample is specifically quantified by the energy difference in the transition from the L to K shells, right? So let's take a look at this diagram and it will become a bit more clearer. So you have the incident electron that knocks off the K shell, right? Electron. So this is lost, or this goes on to do its own thing. Now, when the electron is in the ionized, or the atom is in the ionized state, now an electron from the L1 shell drops down to the K shell, right? And when it is doing that, it releases energy. That the extra energy that is the energy difference between the L1 and the K shell. That energy is released, which knocks off an electron from the L23 orbital, right? So the reason this is a characteristic process is because the exact energy difference between L1 and K is known. So that is a property of that particular element, right? Of that particular electron orbital system in that atom, which is why you know exactly how much energy is being imparted into the L23 electron to knock it off. So you know exactly how much energy this Auger electron has. However, or well, you know the exact energy that the Auger electron has, and that is characteristic of this atom. But in this case, you do know how much energy this electron has, but that is not characteristic of either of the two elements, which is why it behaves as a continuum or white noise in the energy spectrum of the electrons, right? So the Auger process is favored in atoms having small binding energies. Makes sense, because if the binding energy or the critical ionization energy of the L23 electron is too high, then that's going to result. Then most likely the X-ray that is generated, or the energy that is the difference of the L1 and the K, won't be sufficient to knock it off the orbital, right? And then and based on the process that I just described, where the K electron is lost, the L1 electron replaces the K electron, as a result of which the L23 electron is knocked off as an Auger electron, is also called a KL1L23 Auger electron, which is pretty complex in terms of nomenclature. If you recollect, in case of X-rays or characteristic X-rays, we had like the nomenclature was pretty straightforward. You have the alpha, the beta X-rays that are generated depending on what orbital, you either have the K alpha 1 or the K alpha 2 or the L alpha 1, and so on and so forth. And so the other thing is, if you have the Auger electrons that have been ejected from a given orbital, they really do not have a lot of energy, right? Because if you account for the energy difference between L1 and K, and if you take minus the energy of the binding energy, then the energy of the Auger electron is typically about a few hundred electron volts to maybe slightly less than 1 kilo electron volt. So these are really low energy electrons. And if you recollect the plot that I had showed you, which had the secondary electrons and the backscattered electrons in the population of these electrons with energy on the x-axis, then the Auger electrons were somewhere in between the secondary electrons and the upper limit of the energy of the backscattered electrons. Okay, so because of the low energy of the Auger electrons, they make their way out of the specimen only if they are very close to the sample or close to the surface of the specimen, right? So, which makes it very interesting, because now you have a specific set of electrons that you know are being emitted from very close to the surface, which basically means it has a low range in the interaction volume, and which is very important to study the surface chemistry of various molecules, polymers, and organic compounds, inorganic compounds, and mostly samples which are made out of elements with low atomic number, and I'll talk about that later. The other thing is that in order to detect the OG electrons itself, because of the low energy and the low population, in terms of the number of electrons, you need to have extremely high you need to have ultra high vacuum conditions in your chamber, which is not usually available for SEMs or with a tungsten filament. So you are looking at a field emission gun electron column where you may be able to detect the Auger electrons. Okay, so both X-rays and Auger electrons can be characteristic, right? We understood that. Now, which process should you rely on to study a given sample? So, if I give you a sample, would you opt to do an X-ray spectroscopy, or would you do an Auger electron spectroscopy to gather information? And which process you choose is determined by something called the fluorescence yield, which is basically the ratio of the X-ray emission to inner shell ionization, right? So what this tells you is that you have these inner shell ionization that is happening from the electron beam, the incident electron beam, but is that ionization sufficient to generate enough X-rays? If it is true, where the ionization that is occurring in the specimen is sufficient to generate enough X-rays, you would obviously choose the X-ray for your measurement or the X-ray spectroscopy. But if the amount of X-rays generated is not sufficient, then you will have to rely on Auger spectroscopy, right? So if you plot the fluorescence yield, which is also a function of the atomic number, and A is a constant which is specific for the K shell, a number 10 to the power 6, then if you plot atomic number on the x-axis and the K shell fluorescence yield, so this is with the assumption that you're looking at the K shell ionization, you will see that it goes from 10 to the negative 4 to about 1, right? So for higher atomic numbers, for every inner shell ionization, you have an X-ray generated, approximately close to 1, right? So let's take two cases. You have carbon, which has z equal to 6. So if you put 6 to the power 4, A plus 6 to the power 4, you're going to get a number close to 10 to the negative 3, right? So that's your yield. What basically means is, if you are able to ionize 1,000 carbon atoms, you can generate 1 carbon K alpha X-ray. So the yield of the X-ray is very, very low. Whereas, let's take a look at germanium, which has Z equal to 32. You have omega or the fluorescence yield of 0.5. So you can ionize 2 germanium atoms and generate 1 germanium X-ray, right? So you have a higher X-ray generation in case of germanium. So obviously, as a user, you're going to rely on Auger spectroscopy when looking at samples that are made out of carbon. So let's talk about any organic or inorganic molecule. Mostly chemists rely on this when they're doing various synthesis to look at the surface chemistry of their compounds that they make. But if you're looking at semiconductors or high atomic number or high density compounds, you're going to rely on X-ray spectroscopy. Okay, and finally, this is I'm going to talk a little bit about cathodoluminescence, which is very straightforward. Actually, we spoke about the electron hole pair generation while talking about the solid state detectors, right? When we were looking at the backscattered electrons. So as a consequence of the interaction between the electron beam and the sample, you can generate electron hole pairs. Let's take a look at this this figure here. So you have an incoming electron, it hits the valence band, right? And then the valence band has or the sample or specimen has a band gap, right? So this immediately tells you that cathodoluminescence is not something you would do with a metal. It's impossible, right? Because there's no band gap in metals. So you will only be looking at semiconductors or insulators. Okay. which has a band gap. You need a band gap in order to have electron hole pair generation. That's known, right? So as a consequence of this interaction, you have an electron that is that or the energy imparted to the electron is sufficient to move it from its valence band to the conduction band, right? So now you have an electron hole pair. Okay, now, because this is not favorable, an electron from the valence from the conduction band is going to jump back and recombine with the hole, which is the electron hole pair recombination process, and then that results in emission of energy h nu, which is equal to the energy of the band gap, right? So this process is called cathodoluminescence. Now, what you could do as a user is rely on extracting the electrons that were generated as a consequence of this interaction between the electron and the sample, right? So if you are able to do that by applying a bias, so you're actually preventing the electron hole pair recombination. What you're basically doing is electron beam induced current collection, right? Which is also called EBIC. And then, so you basically have a map of the charge that is generated in different regions on the sample as a consequence of the electron beam specimen interaction, which is also sometimes called a charge collection microscopy. Okay, so these are the most general processes that you will encounter or you can do as a measurement in electron microscopes. We spoke about secondary electron generation, we spoke about X-ray generation, we spoke about the characteristic X-ray, the continuum X-ray, the secondary X-ray generation, Auger electron generation, cathodoluminescence. So these are all the different processes that occur at different energy scales, at different locations in the sample in terms of the range and their location in the specimen. Apart from this, there are also other processes called plasmons and phonons that are excited as a consequence of the electron beam and sample specimen or the specimen interaction. But those processes are typically something you will not be measuring in your lab electron microscope, so I'm not going to get into those, right? So with this, I'm going to end the electron specimen interaction aspect of the lecture. In the next class, we're going to talk about how we can detect these X-rays, what are these detectors made of, what is the operating principle of these detectors, right? So please let me know if you have any questions, and we will discuss this later in the class.